Hey everyone, welcome back to my channel where psychology and neuroscience become simple, clear, and actually make sense. So today we are diving into a really important topic called goal-directed behavior. This is all about how your brain decides what you want, what action to take, and how to actually do it. So, for example, deciding to study, choosing to open your laptop, and then physically typing, that's all controlled by the system. And today, I'll break it down step by step so it really stays in your mind. So, let's begin. All right, let's start with the most important concept in this entire chapter, the frontostriatal system. I want you to think of this as your brain's decision making system. So every time you decide to do something, even something simple like picking up your phone, this system is involved. So, what exactly is it? Well, the frontostriatal system is a network of repeating loops that connect two major areas: the frontal cortex, which is responsible for thinking, planning, and decision making, and the striatum, which is the part of the basal ganglia that helps select actions. Now, here's the key idea: your brain is constantly generating multiple possible actions at the same time. Um, so, for example, right now you could be watching this video or like checking your phone or opening another tab, etc. But you only do one action at a time. So the question is, how does your brain choose? Well, that's exactly what the frontostriatal system does. It compares options and selects the most appropriate action for the situation. That's why this system is very essential for things like decision making, goal directed behavior, habits, and motivation, and more, a lot more. Well, now this system is heavily influenced by dopamine, which comes from two important brain areas, the substantia nigra and the ventral tegmental area. So, dopamine doesn't just make you feel good, it actually helps your brain decide which actions are worth doing. So, now let's quickly understand the key structures involved. The striatum has two parts: the dorsal striatum and the ventral striatum. So the dorsal striatum, which includes the caudate and the putamen, while the ventral striatum includes the nucleus accumbens. And then we have the pallidum, which plays a major role in controlling whether actions are allowed or blocked. Okay, so now let's go deeper into the mechanism. So this is where many students usually get confused, so I'll explain it step by step. The striatum is made mostly of neurons that release a neurotransmitter called the GABA, which means they inhibit other neurons. So this system works mainly through inhibition and disinhibition, which basically means turning signals off and on. So, under normal conditions, the pallidum is constantly inhibiting the thalamus. That means the thalamus is being held back and it cannot activate the cortex strongly. So, think of the pallidum like a brake on movement. Now, here's what's happening when the striatum becomes active. The striatum sends inhibitory signals to the pallidum, which means the pallidum gets turned off. And when the pallidum is turned off, it stops inhibiting the thalamus. So now the thalamus is free. It becomes active and sends those excitatory signals back to the cortex, and that leads to movement. So, this is a very important concept that our brain often activates things by removing the inhibition and not just by exciting it directly. Now, another key feature is that these loops reinforce themselves. So, once a pathway becomes active, it strengthens its own activity, and this is called a positive feedback loop. Okay, so in the previous slide, I explained the direct and indirect mechanisms. And now in this slide, I will simplify the two pathways. You must understand this clearly. So the direct pathway helps you perform an action. So it basically says, yes, do this. It works by reducing the inhibition on thalamus, allowing movement. While the indirect pathway, on the other hand, it suppresses the actions. It says, no, don't do this. So it increases the inhibition, making it harder for the thalamus to activate the cortex. So one pathway is helping the desired action while the other is blocking or competing the unwanted actions. And the balance between these two determines what you actually do. Now imagine your brain is considering multiple actions at the same time. The frontal striatal system solves this using something called a winner take all system. So inside the striatum, our neurons actually inhibit each other like constantly. So the neuron that is most strongly activated will suppress the others. So this ensures that only one action wins while all others are shut down. That's why you don't try to do multiple conflicting actions at once. So again, your brain is constantly competing between these options, and only the strongest signals actually survive. Okay, now let's talk about the dopamine because this is where everything becomes really interesting. So, dopamine acts differently depending on the receptor type. So, in the neurons, if we have the D1 receptors, the dopamine excites them. So, it strengthens the direct pathway. But if we have the D2 receptors, the dopamine inhibits them. So, it weakens the indirect pathway. So, overall, dopamine makes it easier for actions to happen or occur, and that's why dopamine is associated with motivation and movement. Now let's connect this to real life. In Parkinson's disease, neurons in the substantia nigra that produce a dopamine start to die. That's sad. So, dopamine levels actually drop, and without dopamine, the direct pathway becomes weaker and the indirect pathway becomes stronger. So, what that means is that the system becomes overly inhibitory. So, what happens is that the thalamus cannot activate the cortex properly, so movement becomes very difficult to initiate. That's why patients show slow movement, stiffness, and difficulty starting the actions. And the treatment often involves a medication named L-Dopa, which increases dopamine levels temporarily. Now let's move into learning. Because this system is not just about movement, it's also about learning what actions are worth doing. So, when you receive an unexpected reward, dopamine neurons fire very strongly. But after learning, something interesting happens. The dopamine signal shifts. Instead of firing at the reward, it fires when you see the cue that predicts the reward. So your brain starts anticipating the outcomes. This is how habits and learned behaviors form. So dopamine also strengthens connections between neurons through something called long term potentiation or LTP. And which means that making those behaviors are more likely to occur again. Okay, so now we divide our system into two parts, the ventral striatum and the dorsal striatum. Our ventral striatum is about motivation and reward that helps decide what you want, while the dorsal striatum is about action and habit, which helps decide what you do. So, first, our brain chooses the goal, then it selects the action to achieve that goal, and this is one of the also important ideas in this chapter. Now let's talk about the prefrontal cortex. So our prefrontal cortex is like the CEO of the system. It helps you plan, focus, control impulses, and make decisions. It also allows you to think about the future and choose actions based on the long term goals instead of immediate impulses. And without it, our behavior becomes impulsive and very disorganized. And that's why our prefrontal cortex is very, very important. Now, let's go a bit deeper into working memory. So, because this is a very important exam point, our working memory is not just remembering something, but it's actively holding and using information that is no longer in front of you. So, for example, imagine you see a light flash on the left side or the right side, then it disappears. So, after a few seconds, you're asked to look at where it was. So, that ability to remember the exact location during the delay, that's what working memory is. And what's amazing is that our neurons in the lateral prefrontal cortex keeps firing during that delay period. So, even though the stimulus is gone, our brain is still actively representing it. And this persistent neural firing is the biological basis of working memory. Now, let's fully understand one of the most important ideas, the hierarchy system. So, your brain does not jump directly from thinking to movement, it works like step by step from abstract thinking to the concrete action. So at the highest level, our prefrontal cortex, it decides the long-term goals. For example, I want to become a doctor. And at the next level, it decides the strategies. For example, I need to study today or I need to study hard. Then at a lower level, the motor system plans the movement. For example, pick up the book. So each of these levels connects to a different part of the striatum. So our ventral striatum, it selects the goals. Our dorsomedial striatum, it selects the actions, and our dorsolateral striatum, it controls the movements. So the system moves from what you want to what you do to how you do it. Okay, so moving on, now let's talk about something very real in our daily life, which is our automatic behavior. So, what are prepotent responses? Well, sometimes your brain wants to respond instantly without even thinking. These are called the prepotent responses. For example, if you see the word red, your brain automatically wants to read it, even if I ask you to say the color of the ink instead. So that automatic urge is strong, and stopping it requires control. This is where the prefrontal cortex becomes extremely important. It allows you to pause, override the automatic response, and choose the correct action instead. So self control is not just a personality trait, it's also a brain's function. So, a classic way scientists study this is through the Stroop task. So, in this task, you might see the word blue written in red ink, and your brain automatically reads the word, but the correct answer is the ink color and not the word. And when the word and color don't match, this is what's called an incongruent trial that your brain has to work harder upon. And our prefrontal cortex becomes more active during this time because it has to suppress the automatic reading responses. So, this task clearly shows how the brain handles conflict and controls behavior. So, another important task is the Wisconsin card sorting task. So, here participants have to figure out a sorting rule, like color or the shape, but the rule suddenly changes without any warning. So, you have to detect that your strategy is no longer working and it switches to a new one. So, this requires flexibility, attention, and decision making, and all these functions are of the prefrontal cortex. And if our prefrontal cortex is damaged, people struggle to switch rules. They keep repeating the same mistake over and over again. And this shows how important this region is for adapting new behaviors. Okay, so now let's look at a darker part of the neuroscience history, which is the prefrontal lobotomy. So in the 1930s, a neurologist named Egis Moniz, he believed mental illness was caused by abnormal connections in the frontal lobes. So he developed a procedure to cut those connections. And then later, Walter Freeman made this even more extreme with the transorbital lobotomy, where a tool was inserted through the eye socket and then it was moved like right and left to cut those connections. And that procedure was very quick but extremely damaging. And then many patients lost their personality, decision making ability, and emotional depth due to this severe procedure. And then over time, this practice was abandoned because of its severe ethical and psychological consequences. And this reminds us of how important the prefrontal cortex is for who we are as individuals. And for those of you who are interested to watch the video more in depth about the lobotomy history, here's the link on my slide, and I'll also put this link in my description box below so you guys could watch this. Okay, so several scientists helped us understand the frontal cortex properly, and thanks to these scientists named John Fulton and Carl Pribram. I don't know if I'm pronouncing their last names right, but correct me. And so John showed that removing parts of the frontal lobe actually changed our emotional responses, while Carl, he emphasized more that the frontal cortex is not just about movement, it's about planning and organizing the behavior over time. And their work helped shift neuroscience away from these destructive procedures and toward understanding the actual brain functions. Now, let me tell you about one of the most famous and important cases in neuroscience, a person named Phineas Gage. This case completely changed how scientists understand the brain, especially the frontal lobe. Phineas Gage was a railroad construction worker in the 1800s. He was known as responsible, calm, and a very good at his job, basically. But one day there was a very terrible accident that occurred. An iron rod, about a meter long, was accidentally blasted straight through his skull and entered below his eye and exited through the top of his head. Now, here's the shocking part: he survived. Physically, he recovered quite well, and he could walk, talk, and function. But something very important had changed: his personality. After the injury, people who knew him said he was no longer the same person. He became impulsive, rude, impatient, and unable to make good decisions. And he also struggled to plan, control his behavior, and think about the future. So, what does this tell us? Again, it tells us that the prefrontal cortex is the part of the brain that was damaged, and it is not just involved in thinking, it is essential for personality, self control, decision making, and goal directed behavior. And before this case, many scientists believed that our brain didn't have specialized functions like this. But Phineas Gage showed very clearly that different parts of our brain control different aspects of our behavior. And for those of you who are interested in watching the short film, here's the link on my slide. And again, I'll also put it in my description box below. Finally, let's talk about connectivity because brain regions don't work alone. The superior longitudinal fasciculus, or SLF, is a major white matter pathway that connects the frontal cortex with the parietal and the temporal areas. So, this allows communication between the regions involved in attention, movement, and cognition. There are different parts of this pathway. We have SLF2 and SLF3. So the SLF2, it connects the dorsolateral prefrontal cortex with parietal region and supports working memory and our spatial attention. While the SLF3, it connects the ventral prefrontal areas and is important for action, planning, and coordination. So these pathways ensure that different brain regions they work together like as a unified system. All right, everyone, that brings us to the end of today's lesson. We explored how the brain selects goals, makes decisions, and then turns those decisions into actions through the frontostriatal system. If this helped you understand the topic more clearly, make sure to subscribe to PsychSphere and support the channel. Drop a comment with the next topic you want to learn or anything you'd like me to improve. I'll see you guys in the next video. Thanks for watching.